Okay, the Cauchy sequence. A Cauchy sequence, in this case for the real numbers in particular, is to be said that for any two numbers inside of the sequence, we said that they can get the close as they want, as we define it in the epsilon, whenever the epsilon is greater than 0, right? If we say these two numbers, the Sm could be so close to Sn, if there exists a number n in the natural numbers, right, that will be basically the bound for all the numbers after that in the sequence. So there exists a natural number n such that these two numbers are greater than n and the absolute distance is less than epsilon. Okay, this is basically the concept of a Cauchy sequence. So, but in the real numbers we have this, that every convergent sequence is a Cauchy sequence, right? And yes, and that actually is true because we have the proof here. So if we suppose that we have the sequence that is converging to S, to show that the sequence is close to any number Sn, for large n and m, we use the fact that they are both close to S, right? So, using the triangle inequality, we give us the following estimates. We said that the difference between them, right, in the absolute value is have to be less than epsilon, but we don't know that yet. So, we apply this technique that we use it also in the limits calculations. We remove S and we apply S, and we have a sum here, an addition here. We can divide this and create, using the triangle inequation, this part, right? So S end is close to S and S is also close to Sm, right? And this two is greater than the original value. So for this, for any epsilon that we have, we should a natural number n such that both they are greater than n, implies, right, that any number that is greater than n will be less than the epsilon divided by 2. Then these two numbers, we can replace it. They will be basically the bounded side of these two. So it will be greater than, but it will be greater than epsilon. In this case, the sequence is Cauchy sequence. That is why I said every Cauchy sequence is bounded. It's coming from this also, right? And also here, this is only for real numbers, that a sequence of real numbers converge if and only if it is a Cauchy sequence. I mean, that is true in the real numbers, and this depends a lot on the completeness of the real numbers from the Bolzano-Weierstrass theorem. Okay, I may get another video for this theorem in specific, but this is not the case exactly when we see more generalized sequence in sets that are not defined based on a distance, but in open sets. So from the point of view of topology, maybe this is not true. However, for the real numbers, it is.